Our topic is exact differential equation. So suppose you have ordinary differential equation in the form of m of x and t dt plus n of x and t dx. Now, if you have this form is equals to 0, now this is an exact differential equation, but before determining that, we will have a test for exactness of the ODE. So the test for exactness of ODE is the partial derivative of m with respect to x is equals to the partial derivative of n with respect to t. So that is your test for exactness. So now, if you know that the equation is exact, so after checking that, so the ODE or the ordinary differential equation is exact if there exists a function f of x and t. So if you have that, so such that the partial derivative of f over dt times m and the partial derivative is equals to m, and then the partial derivative of f over dx is equals to n. So if you have that, so you have the function of x and t would exist. So if this constraint is not true, then this would not work out. So if this is true, now if this is true, then the original ordinary differential equation can be written as m of x and t dt. So we can rewrite that as to plus n x dx is equals to 0. Now we can rewrite this as this. So the partial derivative of f over dt times dt plus the partial derivative of f is equals to times dx is equals to 0. Now the overall derivatives of f is equals to 0. So the overall derivative of f is equals to 0. Then the solution becomes the f of x and t is equals to c. Now, so to understand this, we will try to have some examples. So our example is equals to, this is our example. So x dt minus t dx is equals to 0. So we know that beside dt is m, and then the beside of dx is n. So our m is equals to x, and then our n is equals to t. So before doing this in the method of exact differential equation, we will try to solve this if this is an exact. We will try to use the exactness to check the exactness of the equation. So the dm, the partial derivative of m with respect to x, must be equals to the partial derivative of n with respect to t. Now, the derivative of m, which is the derivative of x, is equals to 1. Is equals to, now, the partial derivative or the derivative of n, which is the derivative of t, is equals to, this is negative t. Our n is negative t. So now the partial derivative of negative t is equals to negative 1. So hence 1 is not equal to negative 1. Therefore, this is not exact. So before doing the method of exact differential equation, you try to check for exactness. So if this is not an exact, so there's no guarantee that you will find a solution by using this method. So next example, our example is t dt plus x dx is equals to 0. We know that besides dt is m, and then besides dx is n. So m is equals to t, and then our n is equals to x. Now checking for exactness, the partial derivative of m with respect to x, that's with respect to x, is equals to, must be equals to the partial derivative of n with respect to t. And then the partial derivative of x, or the derivative of m, is the derivative of t with respect to x. Now we don't have a variable of x here because we are trying to solve for the derivative of m with respect to x. So we can say that this t is a constant. So now the derivative of a constant must be 0. So this is 0. And then next is the derivative of n. The derivative of n is equals to the derivative of x, which is with respect to t. The derivative of x with respect to t, so we can consider this as a constant again. So now this becomes 0. So hence 0 is equals to 0. Therefore, we can conclude that this is an exact differential equation. So now this implies that f of x exists. So the f of x and t exists such that the partial derivative of f with respect to time is equals to m, and then the partial derivative of f with respect to x is equals to n. So now we know that our m is t. So the partial derivative of f with respect to t is equals to t. So now we have this f, partial derivative of f is equals to t, that's dt. Now we can integrate this, integrating that. So f is equals to 1/2 t squared plus g of x. Now why does it has a g of x? Now if we return this into a, if we differentiate this with respect to time, so this becomes a 0. So this becomes 0. So we will arrive at the same equation where the derivative of f is equals to the derivative of t dt. So we will arrive at that. So this is a crucial this is a crucial term, so g of x. Now we can try to plug this into the equation of our d of x, or the partial derivative of f over x is equals to n. Now we will try to before that plugging, we will try to know the derivative of f with respect to x before we can plug that out. So the derivative of f, so the partial derivative of f with respect to x is equals to the derivative of 1/2 t squared. So the derivative of that is equals to 1/2 t squared. That becomes 0 because we are now differentiating into with respect to x. Now this is now we can treat this as a constant. Now this becomes 0. So 0 plus the derivative of g of x, that's the g prime of x. So now your partial derivative of f with respect to x is equals to the g prime of x. Now we can plug this into our n. So that's g prime of x is equals to n, which is our n is equals to, as you know, our n is equals to x. So our n is equals to x. So now integrating this with respect to x, integrating this g prime of x with respect to x, we will arrive at g of x is equals to 1/2 x squared. So we will have that equation. Now we know that our solution must be this. So must be this. The partial derivative of f dt plus the partial derivative of f dx is equals to 0. So we have this partial derivative of f, which is this, and then we have the partial derivative of f with respect to x, which is this. So now your equation, your f of x and t is equals to 1/2 t squared plus 1/2 x squared. So this must be equals to c. Now that is your, so rewriting that, so 1/2 t squared plus 1/2 x squared is equals to c. Now this is your solution. So recap lang tayo. So let's recap. So our equation is t dx. So this is an example 2. This is example 1. So t dt plus x dx is equals to 0, and we know that besides dt is m, so that is m is equals to t, and our n is equals to x. So the partial derivative of x the partial derivative of m with respect to x must be equals to the partial derivative of n with respect to t, which is the partial derivative of m is equals to the derivative of t with respect to x, that must be equals to 0. And then the partial derivative of n with respect to t is equals to the partial derivative of x with respect to t, then this becomes 0. So hence 0 is equals to 0, then the equation is exact. So this implies that f of x and t exists such that the derivative of f over t dt is equals to m, and then the derivative of f over dx is equals to n. Then we will try to solve for the partial derivative of f over dt is equals to m. So we know that m is equals to t. Partial derivative of f over dt is equals to t, and then integrating that, so we will integrate integral of df is equals to the integral of t dt. Then we will arrive at the answer f is equals to 1/2 t squared plus g of x. We have this g of x, so if we try to reverse that into the equation, so if we try to derive that, so we will arrive at the same equation like we have, and then we will try to plug this into the n, which is our n is equals to the partial derivative of f with respect to x is equals to n. So we should know, or we will try to derive this with respect to x. Now the derivative of that, the partial derivative of f over dx is equals to the partial derivative of 1/2 t squared is equals to 0, because we don't have a x here, so we can consider this t squared as a constant, and then the derivative of g of x is equals to the g prime of x. So now we have this partial derivative of f is equal over dx is equals to the g prime of x. Now we can plug this into our equation, which is our derivative of f over x over dx is equals to n, which is our n is equals to x. So the partial derivative of g, or the integral of g prime of x, is equals to the integral of x dx. Now we have g of x is equals to 1/2 x squared, and we know that f of x and t is equals to 1/2 t squared plus 1/2 x squared, and this must be equals to c. And then your final solution would be 1/2 t squared plus 1/2 x squared is equals to c. Now that is your answer. So next, our next example, our next example is 3t squared sine squared x dt, and then plus 2t cubed sine x cosine x minus 2 e to the 2x dx is equals to 0. Oh no. We will try to rewrite that 3t squared sine squared x dt plus 2t cubed sine x cosine x minus 2 e to the 2x dx is equals to 0. Now we know that besides dt and besides dx is m and n respectively, so m and n. So now, checking for exactness, that's the partial derivative of m over dx is equals to the partial must be equal to the partial derivative of n over dt. Now we know that so our m is equals to 3d squared 3t squared sine squared x, and then our n. So let's try to derive this. So dm over, with respect to x, is equals to the derivative of that. So the derivative of this is 3t squared. That's 3t squared. So this is a 3t squared times the 2 sine x cosine x, and then this must be equals to, that's 6 t squared sine x cosine x. Next is our n. So our n is 2t cubed sine x cosine x minus 2 e to the 2x dx. So the partial derivative of m respect to t is equals to, now the partial derivative of that is 3t squared sine x cosine x minus 0. This must be equals to, we have this 3t squared times, we have this 2. So we have this 2. So that must be equal to 6 t squared sine x cosine x. Now our m, now our partial derivative of m over dx is equals to the partial derivative of n over dt. Therefore it is exact. Now this is exact. So the equation is exact. Now we can solve this. So the f of x and t must exist such that the partial derivative of f, such that the partial derivative of f over dt is equals to m, and then the partial derivative of f with respect to x is equals to n. Now we can solve for the m. So the partial derivative of f is equals to dt is equals to m. So partial derivative of f over the dt, which is our m, is equals to 3t squared sine squared x, and then integrating this partial derivative of f over partial derivative of t is equals to the derivative of 3t squared sine squared x. Then this becomes f is equals to that's 3 over 3 t cubed times sine x sine squared x plus the g of x. So we can treat this as a, so now f is equals to t cubed sine squared x plus the g of x. So next is we try to solve for the partial derivative of f with respect to x. So the df over dx is equals to the t cubed sine squared x plus g of x. So the derivative of that is equals to, that's t cubed, because we are now with respect to x now, this becomes 2 derivative of sine squared x, 2 sine x cosine x plus g prime of x. Now we can plug that into our the equation df over dx is equals to 2t cubed sine x cosine x minus the 2e to the 2x, which will become t cubed. So that's 2t cubed sine x cosine x plus the g prime of x is equals to the 2t cubed sine x cosine x minus the 2e to the 2x. Now we can cancel this out. So now the equation g of x is equals to negative 2e to the 2x. Now integrating that, so g of x is equals to negative 2 over 2 e to the 2x, which is g of x is equals to negative e to the 2x. Now we know that f of x and t is equals to our t cubed sine squared x plus or minus the e to the 2x. This must be equals to c. So our equation would become t cubed sine squared x minus e to the 2x is equals to c. Now this is your solution. Okay, so thank you. Good luck.